Hello everyone, welcome to Exploring Technologies. In this video, I will explain about the Adaptive Neuro-Fuzzy Inference System ANFIS. In this video, I will explain its basic theory and its implementation in the MATLAB. So let me show you the content. First, I will explain what is Neuro-Fuzzy modeling. Then I will explain Adaptive Neuro-Fuzzy Inference System, that is ANFIS. Then I will talk about its architecture. Then I will explain its hybrid learning algorithm. Then I will talk about some applications of ANFIS. And then I will show you that how ANFIS can be used as universal approximator. And then in the last, I will explain the MATLAB implementation of ANFIS. For that, I will take the example of the universal approximator. So I will explain all the MATLAB codes and I will show you the execution of the programs. So that will help you to understand the concept. So now let me go ahead. But before going ahead, I recommend you to watch my following previous video that is about the fuzzy logic controller, where I have explained its theory and I have shown its MATLAB implementation. So the link is given in the description. So if you go through this video, it will help you to understand this current video. So now let me explain what is the Neuro-Fuzzy modeling. Before understanding the Neuro-Fuzzy modeling, let me explain the fuzzy modeling and the neural network based modeling separately so that you can compare. So first I'm taking the fuzzy modeling or making fuzzy inference system. Actually, in many situations, it is not possible to obtain the precise mathematical model of system due to its complexity. So in such case of vagueness, ill-defined and complex system models, the one important solution is a fuzzy logic modeling. So due to the rule structure of fuzzy inference system, it is easy to incorporate the human expertise about the target system directly into the modeling process. So building a fuzzy system requires both prior knowledge of fuzzy rules, fuzzy sets, etc., and the manual tuning. That is the drawback actually. So which is really a time consuming and error prone. So FIS are not able to learn. So now let's see what is the neural network based modeling. So in this approach, the artificial neural networks that are low level computational structures are used for system modeling. So here neural networks work well when lots of input-output data for target model is available for training. So obviously they have ability to learn, they can change themselves, but ANN cannot handle FIS-like capability of dealing with the uncertainties, vagueness, and with the human-like knowledge representation and explanation. So that is a drawback of neural networks. So obviously, fuzzy has some disadvantages and neural nets also have some disadvantage. So we are combining them together to exploit their advantages. So to get advantages of both FIS and ANN, they are combined together and that gives birth to the Neuro-Fuzzy systems. So we can say the Neuro-Fuzzy systems are the fuzzy systems with the learning capability, or we can say that they are neural nets that use linguistic information from the domain experts with more transparency. I mean, both the modeling approaches are taking advantages of both the approaches. So we have several combination schemes. I mean, how to combine FIS and ANN together. The first one is the cooperative neuro-fuzzy systems, concurrent neuro-fuzzy systems, and the hybrid approach. In cooperative neuro-fuzzy systems, actually neural nets are used to fine-tune the fuzzy systems. The neural nets are only used for tuning purpose. Okay, after that they are removed and only the fuzzy systems then works. But in concurrent neuro-fuzzy systems, both work together, and hybrid is also a similar approach. So there are many proposed combination schemes with different architectures such as Falcon, ANFIS, FUN, NEFCON, etc. So in this video, I'm concentrating only on ANFIS. So let's see what is this ANFIS. ANFIS is known as the Adaptive Neuro-Fuzzy Inference System or Adaptive Network-Based Fuzzy Inference System. So ANFIS is actually the Neuro-Fuzzy system that uses 5-layer network with supervised learning. It was first proposed by the Roger Chang and Sun in 1994. The link of the research paper is given in the description. You can refer that or you can search on the Google. So this ANFIS is based on the hybridization scheme of AN and NFIS. That is just, I have explained in the previous slide, the third approach. So it has become very popular and has been used in a number of applications since then. So it is simple and very efficient when number of inputs are less, usually lesser than 5. But it suffers with the curse of dimensionality. It means when the number of inputs or the number of membership functions per input increase, then the number of fuzzy rules also increase by this relationship. So fuzzy rules, number of fuzzy rules are equal to the number of membership functions power number of inputs. So if you have, let's say, 2 membership functions for each input and the number of inputs, let's say, are 10, then there will be 1024 fuzzy rules. Okay, so it demands a huge computational efforts. So the computational complexity is the main drawback of the ANFIS when the number of inputs are large. Okay, now let me show you the structure of the ANFIS that was proposed by the Zhang. So this is the network structure which has the 5 layers, layer 1, layer 2, 3 and 4. In the layer 1 we have actually the membership functions. So for the 2 input, this network shown here is for 2 inputs. If the inputs are different, I mean more than 2, its structure will change. And we have 2 membership functions for each input, I mean A1 and A2 for X, B1 and B2 for Y. So if I increase the number of membership functions also its appearance will change. So this is the case of 2 inputs and 2 membership functions for each input. So the layer 1 is actually adaptive layer. That means the values of A1, A2, B1, B2 will change during the training. In the layer 2, it is a fixed layer. The nodes are fixed. So they have the multiplication operation. So the output W1 of this node is obtained by multiplying these 2 incoming signals. And layer 3 is the normalization layer. That's why represented by the N. So here weights are normalized. Later I will show you that how normalization is obtained. And the layer 4 is again the adaptive layer. Here during the training the values are updated. And in the layer 5 we have a single node which is a summation node. So output F depends on simply the summation of all incoming signals to this node. So now let me explain the function of each layer in detail one by one. So first the layer 1. So this is the part of the layer which we have just seen in the previous slide. So as I said, for the 2 inputs X and Y, I have the 2 membership functions A1 and A2 for X, B1 and B2 for Y. So these are the membership functions A1, A2, B1 and B2 for X and Y respectively. So these are the Bell functions. So as I said, the node, every node in this layer is adaptive and the output is given by these 2 equations. So for I equal to 1 to 2, I get mu A1x and mu A2x. Like this, mu A1x and mu A2x. And for I equal to 3 and 4, I will get mu B1y and mu B2y. So I get 4 values for 2 inputs X and Y. So that is actually the fuzzification. So for 2 crisp values, input values X and Y, I get these 4 fuzzy values. So this is the operation. You can clearly understand from this figure that for a particular given value of X, I get these 2 fuzzified values. You can say that the X cuts the membership function at this point. So I get mu A1x. And it cuts the membership function A2 at this point, so I get mu A2. Similarly, I get mu B1 and mu B2y for the given value of y. So this is how the fuzzification takes place. And now, as I said, that membership functions are actually the Bell functions. Okay, so that is the expression which is governing the shape of the membership functions. So here the parameters AI, BI and CI. So these parameters are known as the premise parameters. So these parameters are updated during the training process. Later we will see that how they are updated. Now let's come to the layer 2. So in this layer, every node is a fixed node, as I said, and the label adds pi. The output of the node here is a multiplication of all the incoming values. So obviously the output of the second layer node is Wi, represented by the Wi, where output is simply the multiplication of these two fuzzy values, mu ai x and mu b I y. Okay. So actually the node output represents the firing strength, and this operation is equivalent to the fuzzy AND operation. So it means I will perform the minimum operation. So later I will tell you that what is equivalent to this mu ai x into mu b y. Okay. And in layer 3, this is the normalization layer marked by n. So the normalization is done by this equation. So output of the node in the third layer is represented by Wi bar. So that is equal to Wi upon W1 plus W2. So the current value of output of ith node divided by output of all the nodes. Okay. So that is a normalization of the firing strength. And in layer 4, which is again the adaptive layer, the output of the node in this layer is given by this equation, that is Wi bar, which is obtained from the layer 3 multiplied with Fi. So what is Fi? This is Fi. So Fi is given by Pi x plus Qi y plus Ri. Here x and y are input, while Pi, Qi, Ri are the parameters. So these parameters are known as the consequent parameters, and they are updated during the training process. Okay. And now layer 5. So this is a final single node which is labeled as a sigma, and its function is obviously the summation of all incoming values. So this is how I get the total output, and this is how my neural net works as exactly the Sugeno type fuzzy inference system. So this structure is not unique. We can combine the layer 3 and layer 4. Also the weight normalization can be done at the output stages. So there may be some change in the network. And now let me summarize all those mathematical operations here. So for input x and input y, I get the 4 fuzzy values, as I said. So from this figure, for the particular given value of x, I get mu a1x and mu a2x. So here I get mu a1x, and here I get mu a2x. At this point I get mu b1y, and here I get mu b2y. Okay. So that is a fuzzification. And now in the layer 2, I get the W1. So W1 is the output of the node, and that is simply multiplication of the two incoming fuzzy values. So mu a1x multiplied with mu b1y, mu b1y. Okay. And similarly W2 equal to W2, that is mu a2x multiplied with mu b2y. Okay. So now what I should write here as equivalent to W1. As I said in the previous slide that this operation is the AND operation. Okay, so I will take the minimum out of these two. So just go to this figure and compare mu a1x and mu b1y. So mu a1x is this and mu b1y is this. So which one is minimum? Obviously mu b1y. So my output is mu b1y. Okay. For W2, I have to compare mu a2x and mu b2y. So which one is minimum? Obviously mu a2x. So my output is mu a2x. So That is the expression of W1 and W2. Now the normalization. So W1 bar is W1 upon W1 plus W2. So W1 is mu B1 y upon mu A to x plus mu B1 y. Okay. Similarly, I can write for W2 bar. So that is W2 upon W1 plus W2. So that is mu A to x upon mu A to x plus mu B1 y. Okay. So these are the expressions for W1 bar and W2 bar. Now I can write expression for F1. That is the output of the layer 4. So F1 is simply W1 bar into P1x plus Q1y plus R1, and F2 is W2 bar into P2x plus Q2y plus R2. Okay, and the output is summation of these two, so that is simply F1 plus F2. So from this equation and this equation, if you sum these outputs F1 and F2, you will get output. So this is the actually overall summary of the mathematical operations in this neural net. And now let's see the architecture with the more complexity, where the number of membership functions are increased. So this is one example where the complexity has increased. So here we have the two inputs again, but the number of membership functions are increased. So instead of 2, now I have 3 membership functions. Okay. So when the membership functions are increased, you can see the complexity has increased. So how many rules are there? So fuzzy rules are membership functions, power number of inputs. 3 power 2. So that is 9. So obviously we have the 9 rules, 1, 2, 3, 4, 5, 6, 7, 8 and 9 fuzzy rules. So this is just to show you the complexity of the network. Here is still the inputs are 2. If I increase the number of inputs also, then you just can imagine the complexity of this network. So that is the drawback of ANFIS. So now let me explain the hybrid learning. So what happens during the training actually? So here both side parameters, the premise parameters and the consequent parameters are modified, as I said. So premise parameters are at the input side, those AI, BI and CI, which are actually governing the shape of the membership functions, while the consequent parameters were PI, QI and RI. Okay. So in forward pass, the premise parameters are fixed. Okay. So these parameters are fixed, while the consequent parameters are updated using LSE, least square estimate. And in backward pass, the premise parameters are updated, while the consequent parameters are fixed. And this updation is using the gradient descent. That is known as the membership function fine tuning. As I said, because AI, BI, CI are governing the shape of the membership functions. So during the backward pass, they are fine tuned. So this is the actually the hybrid learning approach. So following are some applications of ANFIS. One is the universal approximator, predictive modeling, that is a time series prediction. Hopefully I will explain this in the next video. The controller design, pattern recognition, data mining, decision making, etc. Okay. So now let's come to the MATLAB implementation. So I will show you the universal approximation example of ANFIS, that how you can utilize ANFIS to approximate any mathematical expression, both in 1D and 2D. So I will take first problem like this. So I have to approximate this equation. I will make ANFIS to behave like a sine function. And in the second example, I will implement this two-dimensional sync function. Okay. So my ANFIS model will behave like this sync function. So what are the steps? In MATLAB, I have to use the two functions, GANFIS and ANFIS. GANFIS is used to create the ANFIS model, while ANFIS is utilized to train that or tune that. Okay. So now let me come to the code. So this is the first file, which is for 1D approximation. I'm in sine function. So first I'm generating the data. So this is my t and this is the sine. So t is the x-axis value and the x is y-axis value. So this is my sine, one cycle. And in the data, I have arranged this t and x like this. So as a column vector, I have arranged. So this is t and this is x in data, right? So that will be used for training. Now generating the initial FIS. So with help of the GANFIS, I will create my ANFIS model. So first I have to define some parameters. So we have the function GANFIS options. Okay. So I'm using the grid partition method. There are other partition methods also. So if you go to the theory as proposed by the Zhang, you will have the better idea about what is grid partition. So with help of the grid partition, I have created this option variable optg. So now I will define the some parameters like how many membership functions I need. Default is 2. So but here I have taken 3. So optg dot, this is actually the MATLAB syntax. You have to write as it is without any change. So number of membership functions 3. Then optg dot input membership function type. I mean which type of membership functions you are taking. So you can take any. There is a list in the MATLAB. So you can take help of the MATLAB documentation. Here I'm taking the generalized Bell membership functions. You can take a Gaussian MF also. Okay. So now with the help of GANFIS, I'm creating my model, my neural net, which has the name ANFIS. Here you have to give the input. So this is the first column, that is input, and this is the output. So it will be treated as input and this will be treated as output for the network. So I have input output data set available for training. Okay, so with help of these options, my network will be created with help of GANFIS, and this is my input and corresponding output. So now I will train this created model. So again, you have some options that you can define during the training. For example, epoch numbers. I mean, how many epochs you want to train. So here I am giving 100. The default is 30. And initial FIS is in FIS. So this is the model which is already created using GANFIS. So these are ANFIS options. So this is the variable which is carrying all this information, OPT. So now this is the function ANFIS, which will train my model. Okay, so ANFIS training is there. So with help of the options defined here, with the help of the data, which is carrying both input and output, the training is started. And after the training, the complete model goes into this variable FIS. So now FIS training is complete. ANFIS training is complete. Then now you can evaluate it. So with eval FIS function, you can find its output for any input. So I'm giving the same input which is taken during the training. Data, I'm in the first column, that is a T column in this FIS. So you will get the output. Okay. So now I am plotting the output. So first I am plotting the actual signal T versus X. And then I am plotting this output, that is the approximation done by the ANFIS. So we can compare. And here I am finding the error. I mean, I'm finding difference between the original sine wave and the approximated sine wave by the ANFIS. So we can see the difference. So let me jump to the MATLAB where I can show you the output of this program. So this is the MATLAB, and this program is already written here. So let me run this program. Okay, so this is the output. So here you have actually the two curves, red and blue. So actual function is the blue and the ANFIS approximation is given by the red. So here you are seeing a single one, but actually they are overlapping with each other. So here I'm taking the 100 epochs and 3 membership functions. So I'm getting very good approximation here. Okay, so both are coinciding with each other. I mean actual function sign and the sign which is approximated by the ANFIS. By just looking this, you can say that both are same, but exactly they are not same. There is some error if you subtract these two curves, and that is the error. So error is obviously in milli. You can see that 2 into 10 power minus 3. So some 10 power minus 3 values. So you can see that both the curves are very, very close to each other. So that is a very good example of that how close is approximation. But you can see the difference. So instead of let's say membership function 3, I can make it 2, and the epochs, let me take it 30. So I have reduced the number of training epochs to 30, and the membership functions per input is 2. So let me run this program and see what is the difference. Okay, so this is the error, and now here you can see the difference. So this blue one is actual sine wave, while this red one is the approximated sine wave. I mean the approximation done by the ANFIS. So ANFIS has trained itself. You understand? ANFIS has trained itself. So for any input t, it will give the corresponding red output. Although it should get the blue. It should give me the blue output, but it will give me the red output with the difference. So at every instant you can see there is some difference, and difference is huge now. So with help of this error you can see at the different instant of time we are getting error up to the 0.08. Although it is very small, but as compared to the previous case where the error was in the milli 10 power minus 3, this is not good. So just by increasing the membership function to the 3 and the epochs number to the 100, I'm getting very good approximation. So that is the output. So here both the curves are coinciding with each other. So I can say that my ANFIS is now behaving as a sine function. So whatever input I will give to the ANFIS, it will simply take sine of that and give you the output. So my ANFIS box, you can say that model or that system is behaving like a sine function. So it means by appropriately choosing number of membership functions and the number of training epochs, I can make my ANFIS to behave like any one-dimensional mathematical function. So that's why I call it as a universal approximator, right? So now let me jump to my presentation back, and here I will take the example of the two-dimensional approximation. So in the previous case I have taken the one-dimensional sine function. Now I will show you can approximate a two-dimensional function also. That is really complex. I have already shown you that I have taken the case of the two-dimensional sinc function. So I am defining the variable x and y, then match grid. Both x and y are ranging from minus 10 to plus 10, and then square root of x square and y square, and this is my sinc function, that is sine r upon r. Here EPS is added just to avoid 0 upon 0, because when r is 0, then there will be sine 0 upon 0, 0 upon 0, so that will be undefined. So the EPS will avoid this error. So I'm plotting this actual function with help of the surf function. Then I'm preparing the data. So I have just because these x and y are two-dimensional, so I have converted them into the columns. Okay, so x is converted into L1, y is converted into L2, L1, L2, and output z is converted into L3. So z is converted into L3. Then L1, L2, L3 all are combined together here to make the data. Okay, so data variable is created, which is carrying all the inputs and output. So in this matrix, the first column is L1, which is carrying the x. The second column L2, which is carrying the y, x, y input, and then z. The third column is z. So these first two columns are input, while the last column is the output. So all input outputs are arranged in this data matrix. And now again the same type of syntax which we have already seen in the previous example. So first with help of the ANFIS we will create the structure, and but before that we have to define its parameters. So with help of the ANFIS options we will define the number of membership functions. We are taking 6 per input, and then we are defining the input membership function type. So here we are taking Gaussian membership functions. Then with help of ANFIS we are creating this model FIS1. So here this is input, I mean the first two columns x and y, and this is output z, and then options defined here. So with this ANFIS option the FIS1 model is created. Now the ANFIS options we will train the model. So this FIS1 is here, initial FIS, and epoch number is 100. So iterations will be done in the 100 epochs. You can change it as per your requirement. And now with ANFIS we are starting the training with all inputs and outputs, and then options given in this line. So once the training is finished, it will take time because it is more complex, because we are taking 6 membership functions and 100 epochs, right? So once the training is finished, this FIS2 is my trained model. So it should behave like that two-dimensional sync function. So for that we have to evaluate it. So with eval FIS, we have given the input x and y to this model, and the corresponding output is this. So ANFIS output is my approximated output, right? So since it is in column matrix, so I have to convert back into the 2 dimension. So with the help of the reshape, I am converting back into the 2 dimensions, and then I am plotting it with the surf. And here I am finding the error between the actual and the approximated plots. So now I will show this into the MATLAB, and then we can have idea how it is working. So this file is already written here. So let me run this. It will take some time because the system is now more complex, and we have defined 100 epochs. So depending on the speed of your computer, it will take time. So let me see what is happening in. Okay, it is still busy. MATLAB is still busy. Yes, it is done. So this is actually error between the actual and approximation. So you can see this is the error, and it is going up to the 0.01. That is also in milli, 10 power minus 3. So I should expect a good approximation in this case. Yeah, I get this. This is actual function, and this is the estimated function. You can see. So both look very similar, but of course there is a difference as we have just seen in the error plot. But they look very similar. Okay, so this is your actual sync function, and this is approximated sync function. So now you can say that my ANFIS model is trained and it is behaving like a two-dimensional sinc function. So if you give any input of x and y, it will create the z output. Okay, and that is equivalent to the finding sinc of input values x and y. So this is one good example. Now let me show you some differences in the input and output. This is the best, I will not say best, but this is a quite good approximation because I have taken the 6 membership functions and 100 epochs. So let me reduce the number of epochs. Let's say epochs are 30 and the number of membership functions are, let it remain 6. So run this program and see what happens. Okay, so this is the error and this is the estimated output and this is input. So it is not good actually. From upside it is looking almost similar, but if you see the downside, there is a difference. Here you can see a perfect circle in the bottom, but here it is not a perfect circle. I'm getting some bounces here, right? Some ups and downs like this. So there is a huge error actually as compared to the previous case when I reduce the epoch numbers. So now let me take one more example where I will reduce the number of membership functions. So I keep membership functions 3 and epochs to be, let's say, 50, and let's see what will happen. Okay, so this is the error and this is the estimated and this is actual function. So you can see that there is a huge difference. So this is my actual function and this is the estimated function or approximation. So this is not matching at all with this input function. As you can see that there is a huge error. So obviously by reducing the number of membership function, it is working very badly. So let me go back to the 6 and epochs to 100. So it is giving me the quite good approximation. Okay, so this is the case where I have taken 6 membership functions and 100 epochs. So this is the actual function and this is the estimated function, you can see. Okay. So that is giving me quite good approximation with very small error like 0.01. So this is how an ANFIS model can be trained to approximate any mathematical expression. So that's why we say it as universal approximator. So in similar way, you can train any ANFIS to work like any mathematical functions. I mean, you can design some controllers also, because controllers are also some mathematical equations, right? So, okay, that's it for this video. I hope you have liked it and you have learned something new today. So thank you very much for giving me your precious time. I hope you will like this video and you will share this video to the maximum. So thank you once again. Have a nice time.